Bismillah Rahmanir Rahim. So today I'll be covering the slope stability analysis topic. The thing about this lecture is that we have already discussed this in our last few classes. So I will be pretty much going over quickly so that we can reach to our main point, that is the last topic where we talk about the ordinary method of slices and the Bishop's method of slices. So we have already discussed that slope stability analysis. If we define slope, so any ground that is making an angle with the horizontal is called as a slope. So if I draw it here, so you see if this is the horizontal, and alpha is called as a slope because the ground surface is making an angle. Initially it is horizontal and then suddenly the angle increases, so that's called a slope. So slope can be natural and man-made, obviously depending on the method of formation, and they can be infinite and finite depending on their length. Actually there is no infinite slope, it's just to differentiate for our analysis purposes. So pretty much if you see the top and bottom of the slope, so if this is the top and this is the toe actually, so if you see the top and toe of the slope, then we call that as a finite slope, and if it is from a part of mountain, then we call that as an infinite slope. So you see here we don't have any starting point and ending point, we just see a certain portion of the slope, so it is referred to as an infinite slope and its analysis will be different. And a finite slope, just example as a dam, so you see this here is the toe of the slope and this is the top of the slope. So this is an example of a finite slope. So after and in our course we'll be covering this finite slopes only. So causes of failure we have already gone through in our lectures, okay, so I'll be just going through that. These are not only but some of the core reasons of the slope failures. And then after that we have already discussed that the types of slope failures. The first one is the slope failure where the failure plane is passing through the slope phase is called as a slope failure, and once the slope slip circle is passing just at the toe of the slope, so that's called a toe failure. Just like this one here, this is the toe and the failure plane, this is the failure plane, there's a probable failure plane where the failure may happen, so that is called as a toe failure. And once this failure plane is coming ahead of the toe, so you see it is ahead of the toe, so that's called as a base failure. So slope failure in which is a special type of the toe failure, okay, where the failure plane is above the toe, but we can call that also as a special type of the toe failure. So these occur, toe failure and slope failures occur in steeper slopes, and one we have appreciable friction, internal friction, that means high values of phi. And what happens at bottom of the slope bulges out. So just like this one here, this was a toe failure and all of the mass has moved out, okay, so this is also called as a rotational slide because the whole mass has rotated forward. This is an example of the slope failure, this is an example of a toe failure, and lastly we have an example of a base failure. So important thing in the base failure is that the topsoil is firmer or stronger and the soil below the slope or the foundation material is of the softer soil. In such cases we have more chances of a base failure. All right, let's move ahead. So coming to the main topic, so in this chapter, as we have already seen our last lectures, that main aim of the subject is to do the slope stability analysis. There are different categories of slope stability analysis. Category A is where we consider different sliding surfaces, so we find out the disturbing moment and the resisting moment, and then we find out the factor of safety by dividing the resisting moment over the disturbing moment. And if the factor of safety is coming to be 1, then we say okay, if not, then we reconsider another sliding surface and do the analysis until the factor of safety is equal to 1. Second category is the limit analysis method, and it deals with the stress strain relationship of the material that is making up the slope and the foundation. And category C is the finite element analysis. The finite element analysis are basically based on softwares because this time we are studying online, so we are having lack of time. Otherwise we could have done some softwares for finding out the slope stability analysis, and most common was the slope W by GeoStudio. That is a very easier method, but there are other example, FLAC and Slide, but the one we could have at least tried one, but we can still see that when you will be coming on campus, so we can discuss that. We can discuss the probability of doing the software analysis for finding out the slope stability based on the finite element method. So coming back to our main topic, that is the sliding surface method. It's category A. So in this method we will be considering three cases. The first one is a purely non-cohesive soil, that means C is equal to 0, and then we have a purely cohesive soils or undrained saturated clays, that means phi is equal to 0, and then we have a C phi soil or partially saturated and mixed soils. So this is how we will be considering three cases separately for the slope stability analysis. So hitting off with the first, okay, let me go there. Alright, that's the first method where we have purely frictional soil, so that means C is equal to 0. So in such soils where C is equal to 0, the failure plane is parallel to the slope face. Alright, and we discussed the reasons that why there would be chances, because the particles will simply roll over or slide over each other. So that's why we have a failure plane that is parallel to the slope face. So if we consider this failure plane here, this indicated by the red dotted line here, this is the failure plane. So if this failure plane and the whole mass above is going to fail, and out of that we consider this element here, weight of the element is W and the slope angle is alpha, so that means failure plane angle is also alpha. And if we divide we resolve the components of weight along and parallel to the failure plane, then it will be this component N that is perpendicular to the failure plane, that is equal to W cos of alpha, and the other component that is parallel to the failure plane is indicated by T, and that is equal to W sin alpha. So you see that the direction of this T W sin alpha is in the direction of the failure, so this is the one that is going to cause the failure. So we can say that this is the one that is going to be disturbing force. And you see, if you remember from the direct shear test, if this is the shear failure plane, so the normal load, if the normal load increases, so the shear strength increases. So that's why we can say that this is the resisting force. So because that weight is perpendicular to the failure plane, so it is trying to press or hold the particles from moving down. So we know that as a factor of safety, we can say that factor of safety is equal to resisting force over the disturbing force. So the resisting force is this N tan is equal to N value. Okay, before that let me do this correction here. Resisting force will be actually the shear strength that is acting at the bottom. Okay, and we know that the formula for shear strength is C plus sigma tan of phi, and because C is equal to 0, so simply we have C is equal to sigma tan of phi. So if we talk in terms of the forces, so it will be normal force into tan of phi. And what is the value of N? N value comes from here. So resisting, so this is the force that is going to resist, Fr. So resisting force is equal to N tan of phi. So N tan of phi is placed here, and from the equation we know that N is equal to W cos of alpha. So plug in the value, so we get this value here. So now factor of safety is resisting force over disturbing force, so that will be shear strength over the T value. Plug in the values, W cancels out, and we know that sine over cos is equal to tan alpha. So this is the equation that we get, that is equal to tan phi over tan alpha. This is for purely frictional soil where C is equal to 0. Now we move to the second case where we have a phi is equal to 0 situation. That means all the shear is coming from the cohesion. So in such soils we always have a circular failure plane where phi is equal to 0, or where we have purely cohesive soils. So the solution to this method to finding out the slope stability of purely cohesive soils was provided by Swedish circle method. So there are certain assumptions that we have to consider while we are dealing with using the Swedish circle method. So as we discussed before, that based on this method, the failure plane is going to be a curved failure plane. All right. And obviously curve is a part of a circle, so we have to see where is the center and the angle subtended by the arc at the center of the circle, that is theta here. So first of all, we are going to find out the weight of the wedge that is going to fail, or that is above the circular failure plane, and we also have to look at the center of gravity. So you see here, this weight W is acting here, that is the total weight of the wedge ABC, and the center of gravity is here, and this center of gravity is acting at, this weight is acting at the center of gravity, which is at a distance d from the center of the circle. So you see here, this weight W into d will be acting in this direction. That is going to cause the failure, because if you see, if the soil moves in this direction, so it is going to fail, this whole mass is going to fail. So this is the disturbing force, WD. All right. And all the resistance, where it will be provided, it will be provided by the shear strength that is shown by the arrow. So this is the direction of the shear strength, and shear strength, the formula is tau is equal to C plus sigma tan phi, but we know that phi is 0 in this case, so simply shear strength is equal to C. So that is the main cohesion. So this is the unit cohesion, C value. So if we want to find out C along the whole length, so what will we do? We will multiply that with L. So L is the length of the arc. L is this length here from BC arc. Okay. So, and if you remember from your maths, you remember that L is equal to R theta. So that is the value of the radius and theta, and this is R value here, that is radius of the circle that is making up the arc. So shear strength will be actually equal to CR theta. So this is the shear force. So to convert that into moment, because it is acting in this direction, so we will find out the resisting moment. MR is equal to tau into R. This is the shear strength into the radius R, because it will be acting in this opposite direction. So factor of safety is equal to disturbing moment, resisting moment of the disturbing moment, and this is the disturbing moment. We just saw that is equal to W into D, weight acting at the center of gravity into the distance to the center of the circle, and resisting moment is equal to C into L into R, so CR theta. So divide that, so this is the equation, CR square theta over WD. This is the case once we have a purely cohesive soil. So this is how we can calculate the factor of safety for purely cohesive soils. If you remember, we discussed in our previous lateral earth pressure classes, we discussed that whenever there is going to be a clay soil, there are chances of tension cracks in that. So if in the same example, if we have a tension crack, then what we have to do is, so it's a little messy figure here because we have been discussing the same lecture in the class. So we know that same rule, that we have to find the factor of safety by dividing the resisting force over the disturbing force. So resisting force is same, but okay, let me rub that and I'll draw that again. Just a minute. Okay, so we know that whenever we are dealing with clay soils, we can have a tension crack. So let's say this is the tension crack that is developed at the surface, and if you remember, the depth of the tension crack is equal to ZC, and it is equal to 2C over gamma. Okay, this is the depth of the tension crack. So we find the depth, and the slip circle will now start from the toe. This is the toe of the slope, and it ends here, because in the tension crack, soil will have no shear strength. So now we have to find out the angle subtended by this arc length BC dash. Its length is L dash, so it's, let's say this angle is theta dash, so length of the arc will be R theta dash, and similarly the shear strength offered will be CR theta dash, and the moment we'll see later on what is the moment. So this is the shear strength for our new case, where the length of the arc has been reduced to L dash because of the tension crack does not participate in any shear strength. So while we are discussing, so we have to consider the worst case scenario. So worst case scenario can be that the tension crack is filled with water. So if the tension crack is filled with water, then we also have a water force acting here, and we know that formula will be W gamma W into ZC, and the force that will be acting here, let's call as PW. So PW is equal to 1 by 2 gamma W into ZC into ZC. So this is the area of the triangle, and that is the force. So now to find out moments, so if we pay attention, so you see there that the weight into the distance moment is acting in this direction as compared to the center of the circle, this one, and this PW is also acting in this direction. So that means this will add up, this water force will add up in the disturbing moment. So resisting moment is the same. So if I calculate the resisting moment, so it will be shear strength into the radius r, because it is acting in this direction. So this will be the resisting moment. So the formula of the resisting moment will be CR theta dash into r. Okay, now we talk about the disturbing moment. So the disturbing moment is, actually we know that is due to the W into D, that is weight, but now we have to add up. So this will be, let's call this PW, that is a force, but we have to find its point of location or point of action from the center of the circle. So we know that in a triangular distribution it acts at 2 by 3rd from the top. So we know that this distance, if this is the ground surface, let me extend that line. So PW is acting at 2 by 3 ZC. Then we also have to find out the distance of the circle from the ground surface. So let's say this is H. Okay, so the total distance, the point of action from the center of the circle of this PW force, let's call that as Z dash. So it will be equal to this H, that is the center distance of center circle up to the ground surface, plus the 2 by 3rd of ZC. So the moment due to that will be PW into Z dash. In this way you will find out the more disturbing moment. They will be considering both the weight disturbing moment and due to the water head developed in the tension crack. So the factor of safety formula will be resisting moment over the disturbing moment, that is CR square theta dash over the disturbing moment will be WD plus PW into Z dash. Alright. Now I move forward. Okay, just a minute. Alright. Okay, so we are here. Okay, so now we have seen the cases where that in case of cohesive soils we have to, just a minute, it's a little bit stuck, sorry for that, because my laptop has lower RAM, that's why it's always messed up whenever I'm using this whiteboard, but I think that consumes a lot of RAM actually. Alright, so after we have discussed that the slip circle for a cohesive soil is going to be a circular form, so this question can come to mind that okay, we know that okay, that's going to be a circle, but why this circle always has to pass through the toe? Because we learned that there are slope failures, there are toe failures and the base failures. So how do we are going to decide that? And then also where the center of the circle is going to be located, from where the arc is forming. So Finite was the person who came up with the solutions for finding out such problems, that where and when the circle is going to be located. Okay, so according to him, he divided all the slopes into two portions. The first portion is that he says that he is indicating slope angle with angle beta. So this is the slope, so this means this is angle beta, that is the slope angle. So if the slope angle is greater than 53 degree, he says that this critical circle is always going to be a toe failure. That means the failure is also always going to be toe failure. So here we are, we know that it's not going to be a slope failure, it's not going to be a base failure, but it is going to be a toe failure. So this thing is concluded for us. So and for angles less than 53 degree slopes, it can be toe failure, slope failure, or a midpoint circle. So we have to choose. So let's talk about first he suggested solutions for the angles that are greater than 53 degrees. So if you look at the figure here, So this figure is for angle that is greater than slope angle that is greater than 53 degrees. So what we are going to do is that we are going to plot our geometry on scale, all right, on any suitable scale. Then we plot a line that is having an angle alpha. So this is the line that is to be plotted, and it is making an angle alpha with the horizontal. And what is that angle? Where do we get that angle from? From this chart here. This chart is for beta is greater than 53 degrees. So if the angle was 60 degrees, so I'll move up and I will find out angle alpha from here. So angle alpha is coming to be, let's say, 35 degrees. So that means in the slope I will place an angle of 35 degrees here if the slope angle was 60 degrees, beta was 60 degrees. Then you see there is another graph that is indicating theta, and theta value for the same slope is almost 37 degrees. And what is theta? You see here, this is 2 theta. So 2 theta will be equal to 37 into 2, that will give us 74. So that means I have to find such a center which extends an angle of 74 degrees from the toe of the slope up to the start point of the circle. Okay, so it's very easy. You just have to know the slope angle, that is beta. Based on that angle, we'll use this chart, and from this chart we'll have the value of alpha and theta. Alpha is the line that we have to make from the toe, from the horizontal, and where it hits the ground surface, that will be the start of the critical circle, and that will be the end of the critical circle. And to locate the center, we have to locate such a center that extends an angle of 2 theta at the arc AB. Alright, so now we move to the second case where slopes angles are less than 53 degrees. So in that case, what we are going to decide, that how the slope is going to be decided, that either is going to be a slope face, either is going to be a toe failure, slope failure, or a base failure. So to do that, we had this person here called as Taylor's. He suggested a Taylor stability number, and the formula for this is given here, is equal to ns is equal to c dash over fc gamma h, in some books indicated with m and some books indicated with ns. So we have to select that which value of failure is going to happen. That will be based using on the stability number. So what we are going to do is that we'll plug in the values of c, gamma and h, and fc is obviously at the failure plane, it is going to be 1. So plug in the values and find out value of m. So from here we can find out the value of m, and we know the slope angle where these two values intersect. So they will tell us that which is going to be the failure case. Okay, either it's going to be a critical circle, through toe it will be full line, if it's below line it's dotted circle, and if it's at the datum, that means at the value of toe, then we use this line. So simply use this chart to decide that either is going to be a base failure, toe failure, or a slope failure. So either if it's going to be a slope failure, then we have to use, if it's going to be a slope failure, we know that we are discussing this time the beta of less than 53 degrees. So in such cases, what we are simply going to do is that we will extend and mark a line that is an angle alpha 1 from the toe of the slope, and from the top of the slope, this is the top of the slope, we will mark an angle alpha 2 from the horizontal where they intersect. So this will be the center of the circle, and this is the radius, this length. Based on the same radius, we'll mark this point. So this will be this end point of the circle, this will be the start of the circle. And where do we get the values of alpha 1 and alpha 2? We'll use this chart here, that based on the slope and based on angle, we will tell us alpha 1, alpha 2, and in between values can be interpolated. So this was a case where we have a toe failure. In a case where we are going to have a base failure, so in that case we are going to use this chart here. So you see in this drawing, there are a few assumptions while dealing with the base failures. Base failure, we assume that the critical circle will pass through a line that is at the center of the slope. So if this is the this is the total width of the slope, that is b, then a line that is b by 2 here, b by 2 from the toe, b by 2 from the top, that means at the center of the slope, the circle will always be located on this line, anywhere on this line. Okay, so there are certain terms. So you see here, this is the circle here, this is the base failure. So the height of the slope is h, that means from top to toe, and there is a term called, this is called d, that is the distance of the hard stratum. This can be rock or hard clay from the top surface. So this is distance d, and h is the height of the slope, and where the slip circle is coming out ahead of the toe, so this distance is indicated as x. So the distance from the toe of the slope up to the point where the circle is coming out on the surface, it's called as x. So so based on to find out the values of these x, what we are going to do is that this is value of beta. We look at the angle here, beta, and then we find out depth factor. So the formula for depth factor is nd. It's indicated nd is equal to d over h. D is this height from ground surface to the depth to hard stratum, and h is the height of the slope. Divide that, whatever value is coming out, then we find out distance factor. It is indicated as nx, and it is equal to x over h. And we just told you that x is the distance, this distance from toe to the start of the slip circle. So we can find out nd from the figure. So where these two value, and we also know the value of the slope angle. So let's say if this is 2 and is coming to be 2 and the slope angle is 40, so that means nx is equal to 1. So put in the values of nx is equal to 1, so that means x is equal to h. So that means that the slip circle will start at a distance of h ahead of the toe. So in this way we can find out the exact position of the circle in case of a base failure. There are certain other methods which also provided by other researchers. Okay, one such method says that if this is if the slope material and the foundation material, so this is the slope material that's making up the slope, and this is foundation material that is at the below the slope material. So if these two materials are same, then what we are going to do is that we'll find out the midpoint line passing through the center of the slope, and the center of the circle will be located anywhere here. So select a point such that it extends an angle of, just a minute, it extends an angle of 133.5 degrees at the center of the circle. So it can be any point. If the factor of safety is equal to 1, then it is a critical circle. If not, then you move the center to the left and then try again extending an angle of 133.5 degrees, and keep on trying until you get a factor of safety of 1, that is the critical failure plane. So this is how we will do the. There's another method of finding out the center of the circle and the slip circle location, but it's very particular that it only applies to the cases where we have same material that is making up the slope and the foundation.